All right, well, today we're going to do chapter 7, but before we get started on chapter 7, we're doing experiment number 7 on Wednesday, and we haven't really talked much about what's going to go on in terms of a flame test, so I thought I'd talk about that for just a minute, and then we'll move on to 7. Any questions before we get started? All right, flame test. In a classic flame test. Now, we might not have to do a classic. We might be able to do something much more fun. But classic flame test, you take a piece of platinum wire, you dip it in a solution containing a metal ion, sodium chloride or whatever, and then stick it in a flame. What you get is a color. And based on that color, you can generally identify the metal ion you're working with. So, let's see how this happens. When an atom absorbs energy, electrons can be promoted to higher quantum levels. So, if we have an atom with various quantum levels going up, and we have electrons in there. We take and we stick this little guy in a flame. It absorbs energy. The electrons can be promoted from where they were up to somewhere else. Now, they're sitting up here at a different, higher quantum level, one that they're not used to, and they have all of this excess energy now. They're going to lose that energy and drop back where they came from. When they do that, the drop is quantized because energy levels are like stair steps, they're quantized. So this drops down, and the energy is released as a photon, but at a single wavelength, depending on how high it was promoted. This one would drop down and produce a different wavelength. This is referred to as an emission spectrum. In the emission spectrum, you have a series of lines, and they're unique for every atom, because the electronic structure of every atom is also unique. For example, you can use something called a spectroscope, like this guy, to look at a light source and break it into the various lines. If we had fluorescent lights on, and we looked at the fluorescent light, we would get something like this. A series of lines, different colors. Again, that's from the fluorescent agents that are inside the lights. Well, when we look at a fluorescent light, we don't see a series of colors. We see white light. That's because your eye is taking all of this and averaging it. That's what happens when you do a flame test. You're getting a series of lines, but your eye is going to average it into a single color. So, this is a classic flame test, like I said. They also have little aerosol cans that are much more fun. You spray it directly into the flame, you get huge clouds of fire and colors. I'm not sure they're going to be in the lab because nobody else uses them, just me. So we'll either do it this way or we'll do it the fun way. One way that we will not be able to do it, sadly, is probably one of the neater demonstrations. Let's see, well, I did this once at UIC. A big lecture hall, 500 people, turn all the lights off, totally black in the room. That's something like this. Such a desperate time.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
Yeah, it's a really neat demonstration, but we can't do this one either. Can't do any of the really fun ones.
Yeah.
Everyone knows what fireworks look like, right? This is where fireworks come from. This is a set of fireworks that was set off in Japan some years ago. But cobalt, sodium, copper, strontium, iron, zinc, and lithium make up the colors. Just mix it in, and you get all this neat stuff. So, any questions? All right, over the weekend, I got an email about STEM Scholars Program. If anybody is interested in teaching, the deadline for this is tomorrow. So it'll be on the recording if you want to look it up and scan anything with it. Also, next Monday, right here, we're doing Chapter 8, Acids and Bases. Please be sure to bring your calculator. And before you bring your calculator, just check it. Make sure you know how to do logs and 10 to the nth, because those are the functions we'll be using. All right, on to aqueous solutions. In this chapter, we're going to talk about dipoles and molecular compounds, electronegativity, polar covalent bonds, dissolution of ionic things in water, solubility of electrolytes, molarity, and finally, dilution. My good laser pointer I forgot this morning, so I'm just pointing blankly at the board, but whatever. Bonding and chemical compounds. We've talked about bonding, we did a whole chapter on it. We said at the time that there were two types that we wanted to deal with. One was covalent, where atoms share electrons, and the other one was ionic, where one atom donates an electron to another. Turns out that these are actually the limits in bonding. Most covalent bonds are somewhere between something like this, where we have perfect sharing because it's the same atom, and this where we have no sharing at all. Most covalent bonds are somewhere in the middle. When we make a bond with something like chlorine, we said we have group 7, so 7 valence electrons, move another one in, and each one lines up with 8. We show this with a dash, and again, if the two atoms here are the same, then this pretty much is a uniform sort of a bond. But most covalent bonds are between different types of atoms, and so they're not uniform. For example, let's look at molecular hydrogen, H2, and hydrogen fluoride, HF. To use this, or to examine the distribution of electrons in a covalent bond, we're going to use something called an electrostatic potential map. Electrostatic potential map is something your computer does for you. So, let's begin with hydrogen itself. For hydrogen, what your computer does is it takes the two nuclei, takes the electrons around it, and you ask it to map where the electrons are relative to the nuclei. And you do this out to about 90-95% confidence level that the electrons will be inside of this shell. So we do this exercise for H2. We generate a shape that looks something like this. Next thing you do is you tell the computer to run a point all across the surface and measure the probability that you will find an electron at that point. Then you color it. If you have lots of electron density, you color it red. If you have very little electron density, you color it blue. And somewhere in between. For hydrogen, to do this process, we wind up with a nice uniform thing. Looks kind of like a line. All right? This tells us the sharing here is uniform. For hydrogen fluoride, we see something totally different. We're going to do the same exercise. We start off just to map where the electrons are. Right away you can see, instead of the line shape, we have something that looks like an egg. When we color this, we see something remarkable. That is, the area down here by the hydrogen is very blue. Up here by the fluorine, we have nice bright red. This is telling us that there is very little electron density around the hydrogen and lots around the fluorine. Compare the two. Obviously, this is an Easter egg, and that's a line. All right, when we have a polar covalent bond like this, we show it with a dipole moment. Dipole moment is actually a vector, but we put a cross on one end to show where the electron deficiency is. The pointy end here is where the electron excess is. The dipole here tells us that there's very low electron density around the hydrogen, and that fluorine is hogging it all. Okay. The reason for this is something called electronegativity. Electronegativity is a magic number, somewhere between 0 and 4. The most electronegative elements are up here. Fluorine is the most electronegative. Hydrogen is over here. It's about 2.2. Fluorine is essentially 4. What electronegativity tells us is that is the tendency of an atom to attract electrons to itself. So, fluorine is robbing the electrons from hydrogen, making a polar covalent bond. All right. Well, this is all interesting and the graphics are cute, but we're supposed to be talking about water, aren't we? Well, water is H2O. Where's oxygen? By George, it's right here next to fluorine. The prediction here is that the OH bond in water should be polar. Okay, let's start off looking at the Lewis structure for water. Lewis structure for water. Oxygen is group 6, 6 valence electrons. Hydrogen group 1, we need 2 electrons per bond, so let's put our 2 hydrogens like this. That is the Lewis structure for water. Now every time I draw this, I draw it with these hydrogens at right angles, if you've noticed. If it annoys you, you could say, gee, why do you do it like that? Why not like this? Well, because this at 90 degrees more closely approximates what water really looks like. Water has a geometry that we refer to as bent. This is the result of valence shell electron pair repulsion theory, which basically says that whenever you have electrons around the central atom, those electrons are negative, and they're going to try to get as far apart from each other as they can. Here we have 1, 2, 3, 4 sets of electrons. 2 are in bonds, 2 are not, but there are still 4. This is what water really looks like when they calculate the bottle. Again, the 2 hydrogens here are on the same side, and these are on opposite sides. The geometry is actually tetrahedral. Tetrahedral geometry, all the bond angles are 109 degrees. The central atom is raised up off the floor, if you will. Not a structure that they teach you in 5th grade, but they should. This is very important in chemistry. All right, valence shell electron pair repulsion tells us that these electrons want to be as far apart as possible, right? If we have a central atom, which is shown here, and we have 2 sets of electrons, the prediction is that we would have linear geometry, 180 degrees. If we bring in a 3rd set, we would get 120 degrees flat. The tetrahedron here, 39 degrees angles, that's what water really is. Any questions? Well, the conclusion here is that water is bent. Okay, the molecular geometry is. Now, electronegativity of oxygen is 3,4. Each hydrogen is 2,2. Our prediction is that these are polar covalent bonds. But since water has a bent geometry, both of these are on the same side. That means that the molecular dipole is going to look like this. We're going to have a positive end here by the hydrogens and a negative end up by the oxygen. If we calculate the electrostatic potential map, that's what we see. Big blue bottom here for the hydrogens, red oxygen. Okay, so water itself is a polar molecule. Polar molecule because of the differences in electronegativity and the geometry. The fact that water is polar is what gives us the ability to do so many of the important things water does. One of them is hydrogen bond. We'll talk about that next chapter. This chapter let's deal with dissolving ionic compounds. Now, an ionic compound, remember, we have a series of ions in their array, and they're held together electrostatically. Very powerfully, actually. Water has the ability to break that electrostatic bond. The process looks something like this. Now, when I click the magic button, animated waters are going to come in and pull off the sodiums and the chlorides in this pretend crystal. And I'll pull them off one by one and carry them off in the solution. So let's just watch the show. There goes the sodium. There goes the chloride. Another chloride, another sodium, another chloride, another sodium, whatever. And the process just keeps going on and on and on. Now I hope as this little movie played, you were paying attention, because the way the water molecules wrap around these ions was different. When we had the anion, water-oriented with the hydrogens facing in towards the negative charge. This tends to take the negative charge and disperse it over the cluster. That makes it stable to go in solution. Over here, the sodium surrounded by waters with the oxygen pointing in. Again, dispersing the charge from a single point charge out to the whole complex. We can use electrostatic potential maps to show that even more clearly. This represents a sodium, white, blue, positive charge, and I've placed 3 waters around it. What I'm going to ask my computer to do is to calculate electron distribution over the whole cluster. When we do that, we wind up with this. Now remember, here in the middle was our big blue ball. It's totally gone. In fact, there's a nice little yellow splotch showing up where the big blue ball is. Water has very effectively taken the positive charge and dispersed it over the cluster. Next chapter, we will look at the same sort of process for a hydronium ion, but we will, instead of using just the water molecules, water tends to run in clusters of 8 to 12. So we will actually do that over the whole cluster and see a remarkable difference. Any questions? Well, let's just talk a little bit about solubility. The term solubility means that something dissolves in something else. Okay. Solubility is associated with a number. At room temperature, 1 atmosphere, magnesium carbonate has a solubility of roughly ½ a gram per liter. That means you have a liter of water, ½ a gram of this, it ought to dissolve. Now typically, you have to stay the temperature. The pressure is not so important. The temperature really is, because at high temperature, things tend to dissolve much faster, much better. Solubility goes up. Solutions that have the maximum amount, in this case ½ a gram, are said to be saturated. But again, that depends on the temperature. Definition, solvent is the thing doing the dissolving. Solute is what you are dissolving. And dissolving. All right. You can cheat on this, though. That is the saturated solution part. Remember, I said when you heat things up, they dissolve better. There are compounds that you can put in water, make a saturated solution, warm them up, and you can add lots and lots more. And when you cool them down, they stay in solution. That's called a supersaturated solution. Take a fries, reasonable fry, supersize, right? Okay. You can get more in than you're supposed to. An example. This is a solution of sodium acetate. Sodium acetate is one of these guys that makes very nice saturated solutions. We heated this up, put a lot of stuff in, cooled it down very, very, very carefully. Because if you so much as breathe on this, it all falls out. Kind of a fun thing to do though. So here is sodium acetate in a supersaturated solution. What we're going to do is drop a single crystal of sodium acetate down here. It'll land about there. That's going to set off mass crystallization. So let's just watch. The second it hits, crystals start to grow. And this is real time. And within just a few seconds, basically this entire flask will solidify with all the sodium acetate that is in there. It also gets quite hot because that's the heat that we put in to dissolve it. When it comes back out of solution, it releases all that energy. So, kind of neat. There's a rule of thumb for solubility. Basically, it has to do with polarity. If we have a polar solute and a polar solvent, they are compatible, miscible is the word that is often used. The rule of thumb is like dissolves like. Polar compounds dissolve in polar solvents. If we have a polar compound and a non-polar solvent, this is oil and water. Do not dissolve. Oil is a very non-polar compound. So like dissolves like. When things dissolve, the solution that you form takes on properties. So if we have ions in our solution, the solution suddenly now can conduct an electric current. That's why you're not supposed to take the hair dryer into the bathtub, right? Because you will kill yourself. Not a good thing. Compound that dissolves forms ions and conducts electricity is called an electrolyte. Compounds that dissolve but do not form ions are non-electrolytes. Now there's a lab that we sometimes do here. It's a classic lab for general chemistry that we did when I was a child. And you simply use a device, something like this, to measure conductivity. Now, we have positive and negative plates, and a little light bulb here. Where do you get the power? Well, back when I was a child, you just plugged it into the wall. Now think about that. There's a solution that can conduct electricity. The light here is, you can notice, is a non-electrolyte. The light is somewhat on. We'll see why next chapter. But we have 110 volts sitting here. in a solution that conducts electricity, and you have college freshmen that have never messed with something like this before. It's an invitation for disaster. If you stick it in something like sodium chloride that makes lots of ions, strong electrolyte, get a big light. There's a third class that's called a weak electrolyte. A weak electrolyte, this is something like acetic acid. Remember, you have to have ions to conduct. Acetic acid can form ions, but with sodium chloride, it's essentially 100% ionized. With acetic acid, it's about 100,000 to 1 ratio. So it is weakly ionized, and you get a weak light. These days, in fact, on the lab that we do here occasionally, we don't use things like this. We have this cute little probe that you stick in, and it gives you a number for the conductivity. For an electrolyte, you get a big number. For a weak electrolyte, you get a smaller number. And if you have something like pure water, when you don't get 0, you get a smaller number than you do for a non-electrolyte. And again, we will talk about why this happens next chapter. Any questions? The conclusion here, very simply, ions, electrolyte, few ions, weak electrolyte, something that dissolves like sugar that does not ionize is a non-electrolyte. Any questions?
Is there a way to, like if you charge the water, and somehow trap it to make the light go on?
Afterwards?
Yeah, like could
No,
you
it's
like
not a
plug it
battery.
in, charge, unplug, and then
Nope.
no?
Nope.
It just
It,
disconnects?
the way conductivity works is you have positive and negative ions that are hydrated, and they conduct electricity by moving from one plate to the other. So that's how it conducts. It goes on a battery. All right. Main emphasis in this chapter is something called molarity. Molarity is simply the number of moles that are dissolved in a solution over the volume of that solution in liters. It's important that the volume here always be in liters. To measure the volume in lab, we will use something like this. It's called a volumetric flask. Volumetric flask has a little line etched right about here. And when you fill this to exactly that line, you get whatever volume. In this case, 1.00 liters. So if we have 1.00 liter of solution, and we have 1 mole in it, that's a 1 mole solution, right? Okay, sorry for that one. Let's go and talk about this. Last week we did chemical reactions in solution. Those were the double replacement reactions. In order to do this quantitatively, you have to know exactly how much of each reactant are in the solutions that you're going to mix. Molarity is what we use to do that. Now, the abbreviation for molarity is an uppercase M. Lowercase m is something that you will encounter in general chemistry, and it stands for molality. which is totally different. They just do that to really mess with you. So just remember, always uppercase M. The way you make a solution of known molarity. You start off with the volumetric class. You need to calculate the moles of the solute you're going to add, and you know the volume of your solution from the thing you're mixing it in. So, we're going to make a solution of known molarity. Here's our volumetric class. You weigh out a certain number of moles and carefully put them in your glass. Once you have it in there, then you add your liquid right up to the 1 liter volume. You know the number of moles, and you know the number of liters, therefore you know the molarity. Simple concept. Let's do a problem. We have 3.25 grams of sodium bromide. This is in 1250 mils of solution. What is the molarity? Well, remember, to calculate molarity, we need to know the number of moles of sodium bromide. And then we just simply divide that by the number of liters. Number of moles. Well, we're given a mass. And by George, we're also given the molar mass, aren't we? We remember, mass over molar mass is a simple way to make it moles. So, this is going to give us our number of moles. We're going to divide that by the number of liters. This was given as milliliters. We divide that by 1,000. And we get 1.25 liters. Now, we look at our equation here. Grams of sodium bromide will cancel. How about moles to the minus 1? Well, minus 1 simply means 1 over mole, right? So what we have here is 1 over moles in our denominator. 1 over 1 over. That's a reciprocal of a reciprocal. If you take something and turn it upside down, that's like a reciprocal, and then you do that twice, you're back where you started. So this is equal to mole. Simply goes back up top. This goes up. Now our units are going to be moles per liter. Simple calculation, 3.25 divided by 102 divided by 1.25, 0.0253 moles over liters. Sometimes people just use uppercase M for molarity. Sometimes it is shown as italic, just to get your attention. Sometimes it's underlined. Sometimes a nice little script version is shown. It all depends on which book you're looking at. I will tend to use simply the M or the underscore, sometimes the italic, whatever. Just remember, always uppercase. Do another one. We have 6.47 grams of sodium acetate. We have 1450 mils of solution. Go ahead and set it up. Once again, we have a mass, and we are given the molar mass. Simple way to calculate moles is mass over molar mass. 1450 mils divided by 1,000, 1.45 liters. Grams of sodium acetate cancel. Per mole goes up top. And we're left here, 0.0544 moles per liter. Sometimes it is written out this way, sometimes with a slash. Again, liters minus 1 is the same thing as liters in the denominator. Let's just do one more simple one here. Potassium hydrogen phosphate. We have 238 grams of it. That's its molar mass. We have a volume of 275 mils. Moles of potassium hydrogen phosphate divided by our volume in liters. Just like that. 238 divided by 174 divided by 0.275. .969 rounds up to 497. Any questions? Nice simple calculation, right? Now there are a couple variations we can do on this type of problem. We'll see those in just a minute. But first of all, let's look at the first tutorial for the chapter, simply called molarity. And it's a table. Again, everybody loves tables. Here, molarity is missing. You simply type it in and check your answer. So, we are given moles, we are given a volume. We know that molarity is simply going to be the moles divided by that volume in liters, which it is. Do the simple calculation. 0.976 divided by 2.15, 0.454 milliliters. Another one. Here the volume is missing. If molarity is moles divided by volume, volume is going to be moles divided by molarity. Volume is moles divided by molarity. 0.666 divided by 0.154. 4.26 liters. And one more with moles missing. Once again, molarity is moles divided by volume, so concentration times volume will give us moles. Concentration times volume, moles. Concentration, volume, moles. Now this that I've been saying over and over again is something that's worth remembering, especially when we do dilution problems. It'll make it simple. If you have a concentration in moles per liter, multiply that by the volume in liters, you will get moles. It's a useful thing to remember. All right. This is just one of the takes on the type of problem you can do. We have a stock solution in the lab here. It's 0.18 molar potassium chloride. What volume do we need in order to have 0.01 moles of KCl. So we're doing an experiment. In this experiment, you need 0.01. We're starting off with 0.18. Again, molarity is moles divided by volume. Volume is moles divided by molarity. In order to calculate our volume, we simply multiply these together. Moles divided by our concentration gives us our volume in liters. Liter comes up top. We get 0.056 liters, but in lab, we would measure this out in liters. Standard sort of problem. Another take you can do on all this. We have sugar, sucrose, and it's dissolved as a 2 molar solution in water. We have 300 mils of this solution. How many molecules is that? So this is going to combine a simple calculation with Avogadro's number. We're going to calculate the number of moles, concentration times volume. Once you know moles, we'll use that to calculate molecules. Again, molarity is moles divided by that. Again, concentration times volume is liters. So, let's just do it. Here's our concentration, here's our volume, everything's in liters. 0.375 moles of sucrose. If we had 1 mole of sucrose, that would add 6 times 10 to the 23rd molecules, but we don't, we have 0.375, so simply multiply the two together. Moles cancel, and we get 2.26 times 10 to the 23rd. Another problem you can do. We have potassium sulfate. You're going to dissolve it in water. We have 150 moles of the solution. How many moles of potassium ions is that? And how many moles of sulfate? Just remember, we need to calculate moles of potassium sulfate. 150 mils of 2.5 moles stuff. Then we're going to use the mole ratio of potassium to potassium sulfate and sulfate to potassium sulfate. Now remember, when we take something like potassium sulfate and we put it into water, what happens is we get total 100% dissociation. So for every 1 mole of potassium sulfate we started with, we're going to wind up with 2 moles of potassium in solution and 1 mole of sulfate. So, first of all, number of moles, concentration times volume gives us moles. .38 moles of potassium sulfate. Then we'll do our mole ratios. For sulfate, there's 1 sulfate per potassium sulfate. So the ratio is 1. Number of moles times the mole ratio gives us 0.38 moles of sulfate. For potassium, the mole ratio is 2 to 1. 2 times 0.38, 0.76 moles of potassium. Any questions? Well, that brings us to our second tutorial, which isn't quite as popular as the first because it's a word problem. And you have to do at least one method conversion in every problem. Here we're looking for a volume in milliliters. Now, if we do classic problem, we're going to get it in liters, and you can multiply by 1,000. We have a concentration, we have a molar mass, and this is the number of moles that we have. Moles per liter is molarity, so moles divided by concentration is our volume. Substitute in 0.666 liters. To convert to mils, we simply take this, multiply by 1,000, and you're at 666 milliliters. One more. We're looking for milligrams. Typically, because the units are in grams, we're going to get grams in our answer, multiply by 1,000 to get milligrams. We have a volume and a concentration. Molarity times volume is going to give us moles. Concentration times volume moles. Simply substitute in, we get 27.9 grams of product. Convert that to milligrams by multiplying by 1,000, and we get 27,900 milligrams. I guess I lied, there is one more. Looking for a volume here in milliliters. Again, we have to multiply by 1,000. We have a concentration, and we have the number of moles. Our volume is going to be moles divided by concentration. Substitute. We get 0.05 liters times 1,000, we're at 50 mils. Any questions? Well, on your exam number 2, there will be 2 or 3 molarity problems. One will look like exactly like the table that we did first. And the other one, well, might look something like this. We have a solution that contains 10 grams of sodium hydroxide. We have 500 mils of this solution. What's the molarity? Well, we know that molarity is simply going to be the number of moles of sodium hydroxide divided by the number of liters. We have a mass and a molar mass. That's going to give us moles. 10 divided by 40 divided by 0.5, we're at half mole. Any questions? We have calcium nitrate. How much of that in grams do we have to dissolve to make 500 mils of a 1 molar solution. Once again, concentration times volume is moles. We have half a liter, 1 mole per liter. That's half a mole. All right, we need to know how many grams of calcium nitrate that is. If we had 1 mole, it would be 164. It's half a mole, so it's half of that, 82 grams. We have a 0.375 molar solution. We have 4.75 liters of it. How many moles is that? Well, this one is very simple. This was an extra credit, actually. We have a concentration and we have a volume. Simply going to solve this for moles. Concentration times volume is moles. Concentration, volume, moles. And 0.78. And our last one. 200 mils of sodium chloride. When we evaporate it, we get out 1.56 grams of sodium chloride. What was the molarity of what we started with? Again, molarity is simply going to be the moles of sodium chloride divided by our initial volume in liters. Moles of sodium chloride is simply mass over molar mass. 1.56 divided by 58 divided by 0.2, 1.33 molar. Any questions? All right, well, molarity is not particularly challenging. Molality is not either. More difficult to work with, more difficult to understand, but that's general chemistry and a lowercase m. So, let's talk about dilutions. There are 2 types of dilutions we're going to talk about. The first one is called a serial dilution. In a serial dilution, you start off with a stock solution of some sort, and you're going to transfer a little bit of it to a beaker containing water. So this is set up where this is 1 liter. We're going to pull 10 mils out, add it to 990 mils of water. In here, that's our first dilution. Our concentration now is 1/10 of what we started with. I'm sorry, 1/100 of what we started with. Well, now we're going to take our second solution here. Take 10 mils out, add it to 990 of water. Dilute like that. We now have a solution that is 10 to the 4th times more dilute than what you started with. Do that again. We get 10 to the 6th minus 6. Do it again. We're at 10 to the minus 8 of what we started with. Now think about that. If I told you I wanted you to make a solution that was 10 to the minus 8 molar, you would have to somehow weigh out a few micrograms and dissolve it in water. Well, you could never do that accurately. But this way you can do it in a serial fashion and wind up with something that is very, very good. This is actually done commercially. Ever heard of homeopathic drugs? Well, they're not regulated by FDA because the concentrations you wind up with are so incredibly small that according to FDA, they don't do anything anyway. So, ever heard of strychnine? Strychnine is an organic alkaloid, it's called. Again, when I was a child, you could walk into a corner drugstore and buy a bottle. 50 cents. Use it to kill rats. Little old ladies use it to kill husbands. Whatever. You just like it on the shelf. You obviously can't walk into Walgreens or CVS now and buy strychnine off the shelf. Too dangerous. But actually you can. Yes, you can. It's a little compound called cold pine. Children's cold pine. So if you have a child and they're keeping you up all night coughing, you can take these little pills, give it to them, won't really do anything for the cough, but it makes you feel good giving them strychnine and keeping you up all night. The ingredients: belladonna alkaloids. Those are really nasty things. Lethal dose is 0.2 milligrams. That's like a grain of salt. Each pill is less than 10 to the minus 14. Yellow jasmine. It's a bush. Has little flowers on it. If you walk through a little field of it, enough will rub off on your legs to kill you. Whatever stock solution they used, they diluted it, 10 to the minus 12 times. And finally, strychnine. Nux vomica is the Latin name for it. It's not a nice thing. This is from strychnine free, it's called. Each pill is less than 10 to the minus 8 milligrams. But you still can give Colcom to your kids, and yes, it is still on the shelves. It's homeopathic. Any questions? All right, the other type of dilution problem. We have a solution of known concentration. We need something else. You take it, you add water, you get a new solution. Standard dilution. The thing to remember when you do a standard dilution, though, is that your volume changes, but the total number of moles does not. Just the volume. The number of moles in the initial solution, calculated as concentration times volume. Final solution, same thing. Volume times concentration, initial. Volume, concentration, final. But initial and final moles are the same. That means we could write this equation: V1C1, V2C2. So, we have sodium chloride at 0.53 molar. We have 500 mils of this. We're gonna dilute it to a final volume of 1750 mils. What is our final concentration? What we're gonna do is simply take concentration and volume initially, and we're gonna calculate our final state. Remember, the number of moles does not change. V1, C1, V2, C2. We're looking for final concentration, that's C2. Here we've substituted, solve for C2, 0.5 liters, 0.53 moles per liter, divided by 1.75 liters. Liters will cancel, and our final concentration is 0.15 moles. Again, very straightforward problem. We can mess with this a little bit. We're looking for a volume in mils. We're probably going to get liters, so multiply by 1,000. We have 2.1 mole solution. We want 1,600 mils of 1.1 mole. Number of moles does not change. Do our standard equation to solve for the initial volume. V1 is what we want. This is C2, V2, and C1. Moles per liter cancel. We get 0.84 liters multiplied by 1,000, 840 moles. Any questions? All right, that's about all that Chapter 7 offers us. We have 3 more tutorials, molarity 1, molarity 2, and dilutions. Remember, we're all chasing 350 points. Also remember, this is the first time I'm telling this officially, but after we finish Chapter 9, we're going to have Amnesty Weekend, so reserve that weekend. On Friday, Saturday, and Sunday, tutorials and quiz 1 will both come back online for the first half if you need to make up something you forgot to do. And finally, next Monday, Chapter 8, please remember your calculator. Make sure it does log instead of dx. All right. I will see you Wednesday for lab number 7.